Hey there, how's it going? So next operation up on the chopping block is multiplication. So when we did the sum or difference of functions and took their derivative, the derivative of the sum or difference of two functions was the derivative of each of the functions added or subtracted together. Okay, so you might think possibly if we have the product of two functions, maybe following the similar pattern, the derivative of a product might be the product of each of the derivatives. So what we'll do is we'll start with an example that we can use existing methods to differentiate, which is framed as a product, and then see if that kind of gut feeling ends up working or not. Okay, so let's start with something like this. So we've got y equals x plus 5, one function, times x minus 1, another function. So of course, we've already done one like this. We can just fiddle with this algebraically first before we differentiate it. So x times x will be x squared. We've got minus x plus 5x is 4x, and positive 5 times negative 1 is negative 5. So now that we've got an expression, which is just some powers of x made with some constant multiples out the front, plus or minus in the middle, we know how to do this. The derivative is going to be bring the power down, subtract 1 from the power, or you should really know a derivative of x squared is 2x, like as you see it by now. And derivative of 4x is 4, and derivative of a constant here is 0. Okay, so let's take a crack at doing this maybe the naive way and think, oh, we've got a product, so let's take the derivative of this product, which is 1, this factor rather, and multiply it by the derivative of this, which is also 1, and 1 times 1 is 1, which is obviously, hopefully, not the same as 2x plus 4, right? So that kind of like logic of extending what we knew about taking the sum or difference, the derivative of the sum or difference of functions doesn't, from this example at least, look like it's going to be that the derivative of a product of functions is the product of the derivatives. So what actually is the rule? Well, let's consult the definition again, right? So let's say we have some function y made up of some function f times g. Okay, so the derivative of this is going to be the limit as h goes to 0 of the difference quotient, where we input x plus h into the function, and we minus the original function, just inputting x into it, and that's all of h. Okay, so that's the product of two functions. Obviously there's invisible times there, and this is its derivative, an expression for its derivative by just using first principles. So just looking at this, doesn't look like there's too much really we can do. There's not really anything you can factor out or anything like that. So what we're going to do is little cheeky trick over here. What I'm going to do is add a term which might help some common factors appear. Say for example, like if we had some term with f of x plus h, then we could take out a factor. Maybe then that would give us something to fiddle around with. And why would I want a factor of f of x plus h to be taken out? Maybe if I can get like g of x plus h and g of x, maybe if I can kind of pair them together with this taken out as a common factor, then I can get an expression for maybe just the derivative of g of x. So what I'm going to do is, well, we're going to end up both adding and subtracting it. I'm going to add this term here, and also subtract it. Okay, so by adding a term and subtracting that exact same term, the net effect of that is adding 0. So I've added 0 effectively, so no real problem with that, right? Adding 0 timesing something by 1 shouldn't really be an issue. Okay, what's the benefit of doing this? Well, now we can kind of pair up some of these terms in the numerator. So what I'm going to do is, there's 3 terms with an f of x plus h. I'm not going to group all 3 of them and take out a common factor, because then this guy will be a bit lonely. That wouldn't be too nice. So I'm going to group up these 2 here. We're going to take f of x plus h outside of g of x plus h, with this term, f of x plus h taken out, minus g of x. Alright, then with these 2 terms left over, well, what have they got in common? They've got a common factor of g of x. Okay, and I'm going to just do it like, put the right hand term out of these 2 first, so plus g of x outside of f of x plus h minus f of x, and that's all over h. Okay, this is looking good because if you have a look at this, g of x plus h minus g of x over h, well, that's the derivative of g of x when we take the limit. And likewise, this chunk over here, f of x plus h minus f of x over h is the derivative of f of x. Okay, so what we're going to do is now do a bit more algebraic fiddling around with this until we can kind of clear these out from each other. All right, so here inside the limit, we're going to have the limit as h goes to 0 of f of x plus h outside of g of x plus h minus g of x, and that's all going to be over h. So that's, at the moment, I'm just going to split up the fraction, right? This term over h plus this term over h plus g of x outside of f of x plus h minus f of x all over h. Now, you might have noticed this conspicuous gap here. So the other thing I'm going to do in the same step is, if we've got the limit, right, this limit here is being applied to this, every single thing here, right? But if we've got a limit of a sum, that's the same as the sum of the limit. So I can kind of just take the limit of this plus the limit of this, okay? All right, so now what we need to do is extract out these bits here. So I'll do this one first. Because we have g of x as a factor there, you might remember when we did the constant multiple of a function, when we differentiated that, we had like just some number k there, and we pulled that number k out, just like I think in the examples, the number I did first was 5. We pulled a number out because if we've just got a constant number, whether it was 5 or some arbitrary constant k, we can pull that factor out as a property of limits. Now, because we're taking the limit as h goes to 0, and this expression here, g of x, doesn't have an h in it, we can, with respect to h, we can treat this function of x as like a constant, right? Because the limit's not being taken with respect to this variable. So we can actually pull out this g of x term, can come outside here. And that's nice because what are we left with here? G of x times the limit is f of x plus h minus f of x all over h. This here is just simply the derivative of f of x, okay? Now, what's going on over here? Well, we can't do the same thing with this factor f of x plus h because we actually do have an h in here, so that's going to pose a problem. But another property of limits, if we have, just like if we had back in, say, before I put that limit there, we had the limit of a sum is equal to the sum of the limits. Likewise, if we have a limit of this product, right, this is the same actually as, say, f of x plus h times this whole fraction here. So if we have a limit of a that times that is the same as the product of the limits, right? So we could break this out as limit of h goes to 0 of f of x plus h times the limit as h goes to 0 of this. Okay, so hopefully this also looks pretty much like that. So this here is just simply the derivative of the g of x function, right? Now, what about the rest of this? Limit as h goes to 0 of f of x plus h. Well, we can actually just straightforward sub in 0 here, right? Why can't we sub in 0, back here? Well, because sure, we can sub in a 0 there, and even there and there, but we can't sub 0 into a denominator. But there's no denominator here. There's no real problem here. We can in fact sub in 0 there, right? Because we would just get, if we sub in 0 here, this bit here is going to become f of x plus 0, and x plus 0 is just f of x. So we've got f of x times, this bit here is the definition of the derivative of g of x, plus we've got g of x times the derivative of f of x. And this is what we call the product rule, right? So if we've got two functions times together, their derivative is going to be the first factor times by the derivative of the second factor plus the second factor times by the derivative of the first factor. So we're basically just going to take the sum of each factor times by the opposite one's derivative, right? So we'll check that with our previous example to see that we get the same thing. Okay, so let's try using the product rule here. We've got our first product here. I'll write it out again. Y equals x plus 5, x minus 1. So this bit here is our f of x function, and it's red. This one here is g of x. So the derivative of this is going to be f of x, right? Let me match up the colors. X plus 5. Where'd that go? Ooh. Times by, so that function, times by the derivative of the other function. So the derivative of x minus 1 is 1. Plus in the middle. Let's be careful. Plus the g of x function. And that's going to be times by the derivative of f of x, which derivative of x plus 1 is just 1. Alright, so nice and easy to evaluate. 1 times that is that, 1 times that is that, x plus x is 2x, and 5 minus 1 is 4, and we get the same thing, so that's pretty nice. Okay, just doing the problem 2 ways isn't enough, so let's do it a third way. So this is fine to remember the product rule this kind of way, but we're going to build on the product rule and do the quotient rule in the next video, which is our fourth remaining kind of basic operation. and it's kind of gets a little bit convoluted to, I think, write in this way. So basically what I want to do is just write this a little bit more shorthand, and also show a little bit of a structure of a way to set it up. So let's just make a little bit of space here. So we can just kind of write this a bit shorthand. It's normally just written like this, that if y equals some function u times v, right, instead of f of x and g of x, then the derivative is u dash v plus v dash u. Now, I've also done something specific here. You might notice I've changed the order. Like, instead of u being use the first factor, but I've wrote the derivative of the first factor first. So I've actually, here I've written this term plus that is this term here. Now, this doesn't matter, right? They're the same, because what's happening in between all these? Well, we've got plus, and order of addition doesn't matter, and we've got multiplication, order of that doesn't matter. However, this order is going to be better, because when we do the next rule, there's going to be a minus in the middle, and the order of that does matter. So doing them in this order is a good habit to be in. Even though it doesn't matter for product rule problems, it will be a good habit for quotient rule problems to just be. You're going to get a very similar expression, so it's better to just get in this habit. Okay, so here again with this problem, we've got y equals x plus 5, x minus 1. Okay, normally with a bit of space, I'd kind of like do this off to the side, so then I can keep doing my derivative down the page in case there's some more algebraic steps after the fact. So I normally do this off to the side, but what we'll do is we'll just identify the first factor, u equals x plus 5, v equals x minus 1, and now we've kind of got two little mini differentiation problems. So the derivative of u as a function of x, so with respect to x, is 1, and the derivative of v is derivative of x minus 1 is also 1. Okay, so what we want to do is do kind of times the derivative of 1 across here. So I'm going to put in like, that's going to times with that, and that's going to times with that. But when I draw this first line in, I normally just go put in a little arrow just to remind me I'm doing that one first. So do this one times this one first, and then that one times that one. This might look a little bit like too much and unnecessary, because you could like identify each of the products, maybe even do this in your head. But the problem is if the each of these factors in the product is like a bit more convoluted, like you've got to use the chain rule and maybe some other extra bits and pieces, you might need to kind of do these little mini differentiation problems off to the side. So once I've done that, I'll then write down, okay, we know, we've got it written up here, y dash equals u dash v plus v dash u. So I'm going to do 1 times x minus 1 plus 1 times x plus 5. And then, of course, expand them out, collect like terms. Voila, same thing again. Alright, so maybe let's just do a fresh problem and also maybe exemplify what I said about, you know, it might be tricky to do kind of just looking at it and remembering the rule. So let's do something like this. Let's differentiate. Okay, so we've got root x times 3x plus 1 all to the 5. Can this in theory be done without the product rule? Yeah, because you could expand out all this and then distribute root x through them all, and then I think you can have just a bunch of terms added together with powers of x and constant multiples. Is it going to be a lot of like board or paper space and probably get some random number wrong somewhere? Yes. So like with say the chain rule, while the examples when we're just doing the power rule are maybe just a matter of convenience, the product rule will be necessary once we start dealing with other types of functions. But matter of convenience, but pretty good matter of convenience if you ask me for this problem. Okay, so we've got our first guy over here, root x. Now, because I know I'm going to have to transfer this into a power, as I write this over here, I'd normally go, okay, root x is, write it with the power, because now that's set up to use the power rule, okay? And v is going to be this one, 3x plus 1 to the 5. Okay, so now we've got to do our little mini differentiation problems off to the side. We're going to have u dash is bring the power down, subtract 1 from the power, and v dash is going to be, so treat the brackets, so we've got a function of x inside the brackets, so we've got like brackets to the power of 5, so how are we going to differentiate brackets with an x inside? To the power of 5, bring the power down, subtract 1 from the power from the brackets. Keep whatever function was inside the brackets inside. I don't know why I didn't just literally write this like a couple centimeters that way. And then times by the derivative of the brackets is the chain rule. So times by the 3 there. Okay, and then we might need to again just maybe simplify these before we actually go ahead with using the product rule. So this is fairly standard as well. Hopefully you've come across this one. 1 on 2, and then actually the negative half. Negative will become a positive power down in the denominator, and just like root x went to x to the half will become root x. And this one over here, we can just do that 3 times 5 is 15. Okay, so now that we've differentiated those little bits off there, we can now find the derivative of this function, which is going to be u dash v times v dash u, obviously using the ones we've bothered to go ahead and simplify. So we can have 1 on 2 root x times this. It's going to be 3x plus 1 to the 5 on 2 root x. And then product rule is plus, and then v dash u. So multiplying across here, we can have 15, maybe root x, and then 3x plus 1 to the 4. Okay, so this expression here is the derivative of this expression here. Now, we could do a little bit of algebra to simplify this bit. Like you might notice 3x plus 1 to the 5 is 3x plus 1 to the 4 times another 3x plus 1. So you can, for example, take out 3x plus 1 to the 4 as a common factor outside of 3x plus 1 over 2 root x plus 15 root x. And then you've got a root x on the bottom. So we could rationalize the denominator by timesing top and bottom by root x, and that 3x plus 1 times by root x on the top. We could keep fiddling around with this. So that's going to be, depending on if you're doing a test or a homework problem or something, that's useful to practice those algebra skills, and depending what's required of you, unless you're just learning for fun or for interest, right? So do whatever your teacher or professor wants, but generally speaking, normally this is sufficient for most kind of purpose that we're going to use a derivative for. Because say, for example, we're trying to find use the derivative, funnily enough, to find the gradient of the tangent to this equation at a particular x value. Well, once we've actually got an expression here, well, we can sub numbers in, right? So it doesn't matter if we manipulate this expression and simplify it algebraically, or take out some common factors, well, if you shove x, some number in for x here, or that other expression, you're going to get the same thing. So that's one reason why it's like, again, context dependent, but why maybe it's sufficient to just get this expression as the derivative for that. The other one would be like, in some contexts we might also want to differentiate this a second time. So this is the first derivative, and we can take higher order derivatives like the second derivative. Well, if the first derivative means differentiate it first one time, or the second derivative means differentiate it a second time, which would mean we just differentiate this function and then differentiate this again. Well, by the time we do all that funky algebra work, we might even make ourselves not even a nicer expression to go ahead and differentiate again. Like, if I had to differentiate this whole function, then I'd probably be alright to go just from this step here, right? So, like I said, depending what context you're doing this maths in, you may need to take out some common factors, rationalize denominators, so on and so forth, get everything over into one fraction, blah, blah, blah. Algebra skills that you should have and be able to use if you need to in that context, but sometimes it's sufficient to just actually get an expression for the derivative. All right. Now, how would we go about differentiating this bit over here? Interesting question. There's a fraction, quotient. That's next video. Catch you later.